Hello everyone, my name is Krishna Shivani and today I will be talking to you about my research on algorithms for robust clustering of multimodal data. Before diving into the subject, I would like to thank my university, Rochester Institute of Technology, and the Honors Program for allowing me to be a part of something so special and innovative, as well as my research supervisor, Dr. Panos Markopoulos, who guided me along every step of the way. So we will first be going over what exactly clustering is and its applications. Then we will explore the early clustering algorithms that set the foundations of modern data analysis, as well as some of the recently developed ones. Next, we will cover a technique to get around outliers and corruption in data, known as robust principal component analysis. And finally, I will share the experimental studies I conducted using MATLAB, which I hope will be insightful and interesting to you all. So, clustering is a widely used technique in machine learning that involves placing data points into categories or clusters. In theory, similar data should be placed with each other in a single cluster, while dissimilar data should be placed in different clusters. Now, when studying clustering, you'll find that it's not just a tool used for a very specific type of data. Rather, it can be used in many different areas of our own lives. From discovering mutual friends for you on Facebook and recommending you shows you might like on Netflix, to filtering out spam mail from your Gmail inbox, clustering algorithms are literally everywhere and make our lives efficient and easy. An important fact about clustering is that it can be broken down into two main branches, unsupervised and supervised clustering. Take this example for instance. We have two clear clusters, the red cluster and the blue cluster. Let's say these clusters hold photos of dogs and cats from some data. A supervised clustering algorithm would require a reference to compare the data to. For two clusters, it requires two references, or in other words, a photo of a dog and a cat, and based on that, it will cluster the given data. Once the clustering is done, the algorithm can tell us that one cluster contains cats and the other contains dogs. However, unsupervised clustering algorithms simply learn the difference by themselves. In the end, they do not end up with the knowledge of which cluster holds which animal because it does not have anything to compare the data to. Now on to clustering algorithms. Quite possibly the most popular clustering algorithm around, K-means clustering has its roots back in the late 1950s when it was first proposed to be used in signal processing. K-means can exactly cluster data, but it's often computationally very expensive to do this, so we resort to the iterative method. So how does it work? Well, to begin iterative K-means, we must initialize K clusters arbitrarily, or in other words, randomly choose K initial group representatives. There is a group representative for every cluster, and their job is to describe the general location of the entire cluster. Now, the entire algorithm revolves around minimizing this clustering objective, which is the sum of all the squared distances between the data and the representatives divided by the number of samples. So to minimize this, we want the representatives to be as close as possible to the data. Once this is done, we assign those data points to the cluster whose representative is nearest to them. Now, because we get a poor clustering from random representatives initially, we calculate the centroids or means of the clusters we created from those random representatives. From here, we continue to reassign points and calculate centroids with every iteration, in turn giving us a better and better cluster structure. Spectral clustering was quite recently popularized in the early 2000s, but has quickly become a widely used clustering method. So in spectral clustering, data is represented as a simple connected weighted undirected graph equal to the ordered pair VE, where V is the set of vertices or nodes and E is the set of all the edges. We then create a similarity matrix W, where Wij equals the distance between the ith and the jth object in the data. The elements of W represent weights that are attached to the edges. Now we begin clustering by attempting to break this graph here into two subgraphs such that the similar or closer nodes are all placed in a single subgraph. Well, two distinct clusters would like to be as different as possible, so we attempt to cut this graph along a line that maximizes the sum of the distances and dissimilarity to get these two clusters here. Now it turns out that the solution to this cut problem is the eigenvector of d minus s, where s is the negative of w, d is the diagonal matrix containing row sums of s, and d minus s is a matrix known as a graph Laplacian matrix. This f eigenvector is an indicator vector where indices with positive values are in one cluster and indices with negative values are in another. Now, for k greater than 2 clusters, we must apply any clustering algorithm to the rows of the matrix formed from the eigenvectors of the k largest eigenvalues. Hierarchical clustering, as the name suggests, uses a hierarchy to cluster data. Using the bottom-up approach, we initially treat each point as a cluster of its own and build up to a single cluster. Now the chosen linkage was average linkage, which essentially means that the distance between two clusters, Ci and Cj here, is the unweighted average of the distances between all pairs of points in both clusters. A nice visual representation of this hierarchy is a dendrogram. Here we see clusters getting merged every step of the way. The height here represents the average linkage between two clusters connected by this link here. And cutting the dendrogram here returns the 4 clusters we wanted, just as in our data. Finally, we have linearized cluster assignment, or LCA, which is one of the more recently developed algorithms and is very similar to spectral clustering. Here we create a matrix C from our similarity matrix W, where Cij equals 1 if the ith and jth object in the data are likely to be in the same cluster, otherwise it equals 0. We seek to permute C in such a way that brings similar objects adjacent to each other and dissimilar objects far apart. From here we create a quantity known as cluster crossing from the sum of the anti-diagonals of C. So here values of this quantity represent cluster separation, while the spikes or humps represent clusters themselves, which is what we see here for data with clear cluster structure with 4 clusters. Now looking only at spectral clustering, we see that it requires EVD to be performed on the graph Laplacian. Sometimes, however, this matrix contains outliers, to which EVD is extremely sensitive. So we look for a way to suppress the influence of these errors by returning an uncorrupted graph Laplacian, which brings us to robust principal component analysis, or RPCA. It attempts to recover L, the corrupted matrix, by decomposing it into R, a low-rank matrix, and O, a sparse matrix, subject to this constraint. So we must deal with the following problem of minimizing the rank of L and the zero norm of S. It turns out though that this is computationally expensive to compute, but this alteration allows us to solve it with ease. The minimization of the nuclear norm of L plus the L1 norm of S subject to this constraint. The pure matrix here is R, and the matrix containing differences and outliers is O. This leads us to our first study, spectral clustering with and without RPCA. A note here is that all studies involving 4 clusters from synthetic data were performed on matrices of size 2 by 200 and 2 by 250 matrices for 5 clusters. New datasets were fed into algorithms every single realization. Now our first study was conducted on the graph Laplacian matrices of data whose clusters had normal distribution, with variance equal to 1 and a random mean. From this we wanted to see how beneficial the effects of RPCA are by corrupting data. Here the x-axis displays the percentage of corrupted entries, which is symmetric corruption to be exact, which simply means that if ij is corrupted then ji must also be, and the y-axis is the accuracy of the algorithm. For corruption, a constant 1000 was added to p-core percent of the entries of the matrix, and there were 500 realizations of this. So we see both algorithms starting out strong, but spectral clustering without RPCA quickly goes down to 60%, or below 60% at a mere 4% p-core. We don't see a significant drop-off with RPCA until 10%, which is almost 1600 corrupted entries. At that point, it's not very surprising to see a drop-off with such a large-scale corruption. Now on to our second study with varying means. The purpose for this study was that we wanted to see how the accuracy of our algorithms changed as we varied the means of our clusters with variance equal to 1. 2 types of datasets were utilized. One was 4 clusters in a square formation where the clusters were centered around these means, while the other was 5 clusters in a pentagon formation centered around these means. All these means were scaled by factors of 1 to 9 with step size 2. So this is a visual representation of the clusters moving far apart. Here are the results for the 4 clusters in the square pattern for 1000 realizations. As expected, we see accuracy increasing. Interestingly though, we notice that HAC has extremely low accuracy for when the clusters are scrambled, but it's very quick to reach the top after. Iterative k-means and spectral clustering with RPCA perform well, and LCA is lagging behind throughout. These are the results for the pentagon pattern clusters. We see the same upward trend for all methods. The algorithms, though, level off a bit later here than in the previous slide, which may be due to the greater number of clusters. Next on to our third study, where we vary the variance of each cluster. The purpose for this study was that we wanted to see how the accuracy of our algorithms changed as we varied the variances of our clusters with unchanging means. The same 2 types of datasets were utilized, but the means of the square clusters were scaled by 5, while the pentagon clusters' means were scaled by 10 to get them as far as possible. The variances of clusters in both datasets were scaled by a factor of 1 to 15 with step size 2. And here we see the disorder increasing along with the variance. From this we'd expect to see a downward trend, which is what we see. For 4 clusters, we notice how accurate HAC is at the beginning and how quickly it drops off. Iterative k-means and spectral clustering with RPCA continue to perform and give satisfactory results, while LCA is yet again far behind everyone. Results for 5 cluster is an identical downwards trend. Okay, now on to MNIST and fashion MNIST dataset. The purpose here was quite simple. It was to see how our algorithms performed on real-world datasets, but due to the enormous size of both datasets, we decided to truncate the data matrices to include the first 4 handwritten digits in MNIST, so 0 to 3, and the first 4 clothes types from fashion MNIST, so t-shirt, trouser, pullover, and dress. And here are the results for 4 digits 0 to 3 in the MNIST dataset. We see iterative k-means and spectral clustering with RPCA performing extremely well with nearly 90% accuracy, with HAC not too far behind, and LCA yet again last. A reasonable explanation for this repetitive occurrence is that LCA is not very good with even mildly overlapping clusters. For fashion MNIST, we see very different results with iterative k-means at 56%, far below spectral clustering with 73% accuracy. HAC surprisingly not only coming behind LCA, but also coming last. Overall, all algorithms are quite considerably underperforming for this dataset. So together, we did a quick rundown for 4 algorithms, learned about how we can get around data corruption, and saw experimental results of how accurate or inaccurate our clustering algorithms were when we applied them on synthetic and real-world data. Something for the future might be to apply these clustering algorithms on other real-world datasets, perhaps from the UC Irvine Machine Learning repository, and possibly even tensor data. Thank you for your time.